Hi everybody, this is Professor Mankowski again, and in this video we're going to begin the quantitative portion of our statistics class, and we're going to start in chapter 2, which is about frequency distributions and histograms. So what is a frequency distribution and what is a histogram? Now, as a statistician, we generally have to go into the field a lot and do a lot of research and get lots of data. So when we have quite a bit of raw data, we have to do something to really quickly summarize that information so we can see trends and patterns in it. And a frequency distribution does just that for us. It lets us take our data and summarize it into a chart form so we can see patterns and make intelligent comments very quickly about what we see happening in the data. And a histogram is what takes the frequency distribution chart and turns it into graphics. There's a lot of analytics we can glean by looking at the graphics that we can't see in the frequency distribution chart. So what we're going to do is start off with a data set here. And the data set represents the highest temperature any state ever had recorded, all 50 states. And what we need to do, the instructions ask us to create a group frequency distribution for the data using 7 classes. So before we get fancy and sophisticated, if we were to just take a look at the data for what it's worth, just at face value, what kinds of observations can we make? We can make a few comments. We might be able to detect that the maximum temperature is 134 degrees, the minimum is 100, and we have a few temperatures that are even repeated, like 117 degrees. And we have some temperatures that appear more similar to others. I mean, some temperatures that are more similar than others are. So what the frequency distribution chart is going to do for us is it's going to take similar temperatures and it's going to group them together into buckets. And then we're going to be able to count how many temperatures are in each bucket. And we get a really nifty analysis that we can do from doing that. So in order to start out, there's some definitions and terms we need to know. First thing is called classes. Now, a class is going to be equal to the number of buckets that we're going to end up having for our data set. In this case, we've been asked to use 7 classes. And the second thing that we need to know is we're going to hear the word observation over and over again. Observation refers to one individual data value. The end product of what we're going to end up with is going to be a histogram. So let's take a quick look at the histogram to see what this is going to look like when it's finished. And what the histogram is going to be telling us is that if we take a look, we might see that there were about 18 states, for example, that had a high between 109 and about 114 degrees. If we look on the far left, about two states had highs in between 99 and 104.5 degrees. And what we're also going to end up doing is finding out that the shape of the histogram can alert us to a lot of really special intelligence pieces of information, a lot of intel about what's going on in the data set based on whether we detect our shape is skewed left or skewed right, or bell-shaped or uniform shape. It lets us know in later stages of analysis exactly what kinds of analytical techniques can be used on a data set and which ones are out the window. Okay, so how do we get started on building that frequency distribution? The very first thing that we have to do is calculate the range of the data set. And to get the range, we're going to take the maximum and subtract from it the minimum. We can find that the maximum is 134. The minimum is 100, and that's going to give us a range of 34 degrees. Next thing we're going to do is we're going to take that range and we're going to divide it by the number of classes. And remember, the number of classes is going to come from the question, so it's not a formula or anything like that to get the number of classes. In our case, we're going to take 34, we're going to divide it by 7. We're going to get 4.85, and we're going to round that up to 5. Now, always round up. There's a reason why we're always going to be rounding up, never down. Like even if you ended up with your class width of 4.001, still round it up to a 5. Now, something else that you need to make sure you remember is make sure that your class width ends in an odd number. So if you ended up doing your calculation came out to be 3.1, you rounded that to 4, round that up again to a 5. The reason for that has to do with something that we're going to end up seeing happen later on when we do the frequency distribution chart. Now, once we've got our class width, we're essentially ready with everything we need to do to start building our frequency distribution chart. So first thing that we're going to do is we're going to make a column for class, and we're going to number 1 through 7 because we have 7 classes. And I'm going to go ahead, I'm going to write in classes for lower limit and upper limit. And what those two are going to tell us eventually is what's the starting and ending temperatures that each class or each bucket is going to end at. Remember, the different classes essentially correspond to the different number of buckets that we're going to have for the data set. We're going to be counting up how many temperatures fall in each bucket or each class. So to get the lower limit, what I'm going to do is I'm going to go and I'm going to put in the minimum number in the data set. And I can get that right off of my range formula. That's going to be 100. So I know that that first class will eventually tell me how many temperatures we had between 100 degrees and some higher number. Right now, I'm not going to worry about the upper limit of class 1 though. Instead, what I'm going to do is I'm going to get the lower limit of class 2, and then I'll be able to use all the lower limits together to figure out what the upper limit should be. So for class 2, I'm going to take 100 degrees, my lower limit for the preceding class, and add to it the class width. That's going to give me 105 degrees. I'm going to follow the same exact pattern for all the other lower limits. And then I'm going to start to figure out the upper limits. So the upper limit of class 1, I need to figure out how to get that. And all I really know right now is that the starting point of class 2 is 105 degrees. But I don't want to make my upper limit of class 1 equal to the upper limit for class 2 because that could get me in trouble. So what I'm going to do to prevent any overlap is I'm going to take 105 degrees and I'm going to subtract exactly 1 from it. That's going to get me to 104 degrees. Now, the problem that could save me from potentially is if I had a data value that was actually equal to 105 degrees, and the upper limit of class 1 I put at 105 degrees, technically I wouldn't know if that data value should go in class 1 or class 2, and that could really screw up my analysis. So anyway, now that I have my upper limit set at 104 degrees, I'm going to go ahead and I'm going to pencil in all the remaining upper limits for the other classes by taking the same procedure. I'm going to take, for example, class 2, I got at 109 degrees by taking the lower limit of class 3, which was 110, and subtracting 1 from it. Now, that'll bring me all the way to the upper limit for class 6, but how do I finish the job? Because I don't really have class 8. So how do I figure out what the upper limit of class 7 should be? Well, I'm going to pick up on the pattern where I seem to have added 5 each time to get the upper limit. So I'm going to keep on using that pattern. I'm going to put in 129 degrees plus 5 equals 134 for class 7. Now, one thing that might happen that can confuse you, you don't have to worry about it, is you might not end up equaling the maximum of the data set when you're at the upper limit of the last class. Most of the time, we probably won't equal it, but that's why we're doing the funny rounding techniques when we're calculating class width. We're trying to get the upper limit to come out to equal, we're trying to get the upper limit of the last class to equal the maximum of the data set, or at least come as close to it as we can. Okay, so now that I have my upper and my lower limits, what next? Next thing I'm going to do is calculate my lower and upper bounds. And when we put them in the frequency distribution table, we won't actually be able to analyze the information at all in the frequency distribution, meaning right now they're useless columns to us. Where we need them is when we do the histogram. So to get my lower bounds, I'm going to take the lower limit of each class and subtract exactly 0.5 from it. To get the upper bound, I'm going to take the upper limit of each class and add exactly 0.5. And I'm always going to be using 0.5. That won't change unless I end up with data that has decimals. For our purposes, we're only going to be working with whole number data sets though. Okay, so now that I have my upper and my lower bounds, what I'm going to do is I'm going to remove those. I'm going to use them again. I'll bring them out when I start to build my histogram. Right now, I'm going to remove them just to clean things up. And what I'm going to start to work on is my frequency. So what my frequency is going to be doing is it's going to be telling me how many temperatures I have class per class. So class 1, I want to know how many temperatures were between 104 and 100 degrees. That's what my frequency is going to tell me. To get class 2, the frequency is going to tell me how many temperatures were between 105 and 109 degrees. And students get really challenged when they're trying to figure out the frequency because they're looking for some formula or some kind of crazy calculation to do to get the frequency. But it's really much simpler than that. All we have to do is go into the data set and manually count up the corresponding temperatures for each class. So class 1, I know I need my frequency to tell me how many temperatures are in between these two numbers. So I'm going to go in the data set and I find out that I got exactly 2 temperatures. So I'm going to go ahead, I'm going to write in 2 for my frequency count. For class 2, I need to know how many temperatures were between 105 and 109. And if I circle all those values, I end up with exactly 8. Now I'm going to do the same exact thing for all the other classes. And in the end, I've got a column with everything I need to know. Now, before we start to analyze this, something really important that's going to save you a lot of trouble, add up your column and see if you total the number of observations in the data set. Now, in our case, we total 50, but if it turned out that you were doing a whole presentation on this and somebody in your audience notices that your frequency column totaled up to 31 or 62, all of a sudden you've got a lot of explaining to do. And you don't want that to happen. You want to make sure your data is valid before you start to do an analysis. So fortunately for us, we checked out to 50. That is not going to happen. We're in very good shape. And now we're ready to start analyzing with our next column. Now, when we were looking at the frequency column, we were able to tell, for example, in our third class, that we had 18, which was the most states in class 3 between 110 and 114 degrees. But we don't really know, how much of the pie was that. Like we know it's where most of the data was, but how much of the data, what chunk of the data was that? And calculating something called relative frequency will give us exactly that answer. So to get the relative frequency, what we're going to do is we're going to take the frequency for each class and we're going to divide it by our total number of observations. So for example, class 3 comes out to be 36%. That lets us know that nearly half the data, 36% of it, is in between 110 and 114 degrees. So there's a 36% chance that your state had a high in between 110 and 114 degrees. There's a 4% chance that your state had a high in between 100 and 104 degrees. So it gives us a lot of really nifty information where we can start to get into probability too. Now, something else that we might wonder about, by the time we climbed up to 114 degrees, notice that it appears we're almost at half the data because class 2 was 16%, class 1 was 4%, class 3 36%. So something that we can use to help us quantify like the ongoing accumulating total is going to be something called cumulative relative frequency. And it helps us do some really cool analysis with the data. So what is cumulative relative frequency? When we think of the word cumulative, cumulative to us right now in statistics means the same thing it does in everyday language. We think of cumulative of keeping a running total. That's exactly what we're going to do when we create our cumulative relative frequency column. So I'm going to go in each class and I'm going to look at how much data, what was the percentage that came before that. I'm going to start adding it all up. Now, class 1, I need to know how many temperatures, what percentage of data was less than 104 degrees. Well, right now I know that's only 4% because class 1 was just the first class. For class 2, which percentage of temperatures were less than 109 degrees? Well, what I can do is I can take the frequency, rather relative frequency that I have for class 2, 16%, and add that to the cumulative relative frequency of class 1. That tells me 20% of my temperatures are less than 16 degrees. Class 3, I'm going to take 36% and add that to the preceding percentage that I just calculated of 20%. So it's telling me more than half of my data is less than 114 degrees. So more than half the temperatures are below 114 degrees. I'm going to keep on doing this all the way down. And if I did a really good job, I'm going to end up getting to about 100%. So now that I have this all calculated out, what I'm going to do is I'm going to start to put this back into a chart to summarize it really nicely. And there's something really cool that I could do with the cumulative relative frequency. If I focus in on, I'm going to just pick class 5 here, 96%. Imagine that we repeated this study, like we got new data in 2 years from now, and the cumulative relative frequency for class 5 changed, and it was, let's say, 40%. What I want you to think about is, if it was 40%, would that be an example for global warming or against global warming? Which one do you think? Would it mean that the Earth is really starting to freeze down, or it's really starting to boil up? Which one do you think? Now, the answer is, it would mean global warming is happening, because if 40% of our temperatures are less than 124 degrees, what does that imply? It means that most of the temperatures, more than half of them, are rather above 124 degrees. So that means things are really sizzling up on the planet, and we have this massive heat wave that's rolling through, and that's staying with us. Okay, so now that we have all of our different columns here, what we're going to start to do is we're going to start to create our histogram graph. And what the histogram is going to do is it's not going to take all of the columns and turn it into graphics. Don't worry. We're primarily concerned with the limits against just the frequency. Now, here's what we're going to start to do. We're going to start to work up the idea of how to put the frequency, the histogram together, but then we're going to make a change in it. So I'm going to get ready by creating a graph here. On my x-axis, I'm going to get ready to pencil in temperatures. My y-axis, I'm going to start to get ready for frequency. And my first class went between 100 and 104 degrees. I'm going to raise that up to the frequency height in just a moment. What I'm going to do next, though, is put in all the upper limits, or I'm going to start to put in all the upper and lower limits for the next classes. So we're going to go ahead and we're going to put in the first class went up to a height of about 2. The second class went up to a height of 8. The third class went up to a height of 18. Now we could keep on doing this. Technically, we could load up all the bars for all 7 classes. And it seems fairly straightforward, but we create a kind of a big problem if we keep going like this. And here's what could potentially get us messed up. When we have a really big data set, meaning like if we had 20 or 30 million temperatures in our data set, we're going to have a whole bunch of classes, maybe 500 or 600 classes. And we're going to end up with a lot of dead space in between those bars. If we're trying to do a graph of 300 or 400 classes, that means our graph is going to stretch and stretch and stretch so wide, it's going to really hamper our visual analysis. So what we have to do is do something to get rid of all those blocks, rather not the blocks, but all those spaces of air in between the blocks. So how do you do that? Like, how do you close out all the air in between those blocks? Our answer is that's exactly what we're going to use our lower bounds and our upper bounds for. And it's going to help facilitate our visual analysis. So just to make sure that we can eyeball properly what's happening here, our first class went between 99.5 and 104.5 degrees. So right here, we've got graph telling us that we had about 2 temperatures that were in between 99 and about 99.5 and 104.5 degrees. The next class is coming in right here. We've got about 8 states that had temperatures in between 104.5 and 109.5 degrees. So now that we have the idea how we did the histogram, what we can do is compare the shape of that to the different graphs that we talked about at the onset of the lesson. And the reason why we do that is because by determining what graphical shape our data seems to portray, that really helps us out in later chapters when we're trying to figure out what analytical techniques are the right ones to use on the data set. In this case, we probably come the closest to having bell-shaped data.